equals r theta. Or area of a sector, you would write 1/2 r squared theta, okay? So you're not going to have to work anything out on the memo page, quizzes, other than like sine of 11 pi over 6 kind of stuff. So it's just quick, like, do you know it? Okay, so area of a sector. You have two choices that you probably were faced with on your homework. Like, did you want to find the whole circle in degrees and then take a portion of that circle and figure out your fraction? That works. Or you could go straight to the area of a sector is 1/2 r squared theta, and you would, as long as you do this in radians. Arc length. Now, girls, in calculus and BC, or those of you that go to Cal 2 eventually, an arc could also be something like a piece of a sine wave. Do y'all see what I mean right here? That's an arc. Do y'all see that arc right here? I'm sorry, let me do it in red so you can really see where I'm writing. Do y'all see this down here? You don't have to write right now. I'm going to step away. I want y'all to listen just for a second, okay? I know I've already put the box there, but I know the rules. Sorry, I'm breaking the rules. Do y'all see that this is a little piece of an arc right here? Okay, when I'm talking arc length right now, I'm talking about a piece of a circle for sure. All right, I'm talking about this kind of thing right there. The hardest way to do it, which is not horrible, is find the whole circumference of a circle and then take a fraction of it based on the angle that you have. One thing that Grace recognized in the last class and that I made an emphasis of, is that circumference is 2 pi r. That's how you find the arc all the way around. All the way around like this is 2 pi. And so she reasoned if I gave her 30 degrees, all she had to do was say pi over 6 times the radius. That makes common sense, okay? If you need a formula, you can just quickly use S equals R theta. It's a great lesson and why radians are so nice, because it's really based on the circle that you're working on. It's already built in. Hopefully, okay, now you can write them on your memo page if you haven't already. Did some of y'all use these formulas on your homework? Yeah. If you didn't, you would have wished you had. If you did, it felt like really aggravating drill after a while, probably.
So I have a question.
All right, Nicole?
Are each of like the little I guess you know how on the sine graph it's like this part, is that like a semicircle, or is that how much of a circle is that?
It is. It's going. That's a great question because it's coming off of a circle that's being unwrapped. You know, I've shown you that rolling circle and it's being unwrapped, and no one's ever asked me that before. So, yes. Let me think. Let's look at it together, Nicole. Have y'all got that down to where we could go to something else? What Nicole's asking me is, as we there's an animation that I've shown you where the circle's rotating around. And then it shows you starting to roll away. Do y'all know what she's talking about? Let me pull up that animation. It's good to look at for today anyway. Oh, this is the one with the dramatic music, I think. Let's see. So we'll have the dramatic music. Because it's not making a semicircle. Look at it, Nicole. And we'll talk about why. All right, hang on just a minute, and we'll talk about it. I don't really care about the backwards. Let's see if it goes again with the forwards. If it doesn't, I'll restart it. Or whatever that is. All right, so let me go back. It's important to our discussion today about linear and angular velocity. So as this wheel turns, do you see how it covers ground and it leaves that behind? the distance that it covers will be based on the tire. All right, now let's look at, let me pull up something else while I'm here. How do you spell bicycle? Oh. All right, we'll come back to this in a minute. All right, now let's look at it, Nicole. If I'm graphing y equals sine x, okay? We've talked about that you could go around the circle like this, and that right now you have no y component. Do y'all see what I mean? So the sine of 0 is 0. And then the sign grows and goes up to 1. And then it shrinks to 0 again. But I think what's happening here, if we look at it, is that it takes pi radians for it to go up to 1 and come back down.
Yeah.
And so at pi over 2, it's up 1. So as it's unwrapping it, that little piece is really not a semicircle. What a great question, though, because it can be out. Like right now, I'm thinking out loud because no one's ever asked me that before. But it's going around like this. But if we're looking at it, it doesn't really look like a semicircle other than I just accidentally sort of drew it like that. But if it was a semicircle, then this is pi. You see this blue? This is pi, 3.14, and this is 1. Do you see what I mean?
Yeah.
So the radius this way is about 1.57. That's pi over 2.
So it's not.
So it's not. But it's really interesting to think about what's happening as we unwrap it. Because it's still going up 1 and down 1. It just, here's the answer. This is now unwrapping over time. And so we're really graphing where it is over a certain period of time. And it takes 2 pi radians for it to finish that cycle.
But it will still go up the same.
It'll go up whatever the amplitude is,
Yeah.
whatever the radius of the circle is. Okay? Zaina?
So if one full sine, period, I guess, like one whole sine graph thing is equal to the circumference of the circle, and then half of that is just one part, like equal to the measurement of a semicircle,
Right.
but it's not shaped as the semicircle, right? Like it's not an exact.
Right. Not when you stretch it out and graph it.
Right.
Okay? Because I wonder if we had a slinky here for a while.
Yeah, I love slinkies.
I don't see one there. But anyway, what I was looking at right now, Zaina, is when you start to stretch, now we could make one that's a semicircle if we change the period to be 2.
Yeah, I realize
Then it
that's
would
actually
be-
not a great question.
No, it's a great question. I've never sat and thought about it before, but when you're graphing them and you're not making these little semicircles, you could make that happen, but you have to change the period. Okay? Because now all of a sudden you're graphing it over
So then,
time.
like your period would have to be the same.
And
as
so
your
a
amplitude,
time
right?
could be real stretched out for that thing to roll over.
Yeah, so it's like your period would have to be the same as your amplitude. Then.
Right. Or half of the period would have to be the same as the amplitude. Okay? Great question. But now that you and I are, all of a sudden you're making me think about it, is time could be all sorts of different things as it stretches and shrinks. Okay? So this is the length of time it takes it to happen. All right, girls, do you really, really, really want to listen? Shh. Okay, great discussion. All right, now I'm just trying to pull up, here we go, this is great. That's pretty funny. All right, we'll just look at this one. Right. That's crazy. Um, we'll take this crazy one right here. I'm afraid that's Pee Wee Herman, though. I don't want him. Okay. It is Pee Wee Herman. Why is Pee Wee Herman on here? Here, we'll take this. All right. Which is pretty remarkable, actually. That's crazy. All right. Okay. So, how is this dog going to be riding that distance? Just wait. Don't answer the question. It was a rhetorical question, okay? But if there was mud on the ground right now, which I'm sure, like the other day, I pulled up some tracks in the snow. If I pulled up mud or it was raining and there were tire tracks behind it that it was leaving behind. So this is where it's come from, the dog riding the bicycle, okay? And then it's going to continue on. Distance would be maybe it went, the bike went a certain distance per hour, like miles per hour, feet per second. All right, the distance that it goes, just the miles, would be from this. Do y'all see this right here? As that bike rolls, isn't this going to lay down this track on the ground? If this was muddy, you would actually see this line behind where this dog was riding, right? Okay? And then as it continued to ride, you would see that also happen. I don't know if you've ever seen when they actually paint the streets. They get a wheel wet with, I don't know what they do today. They probably maybe have something more. Well, I did it when I was coaching varsity track and cross country. We wanted to go to the park and get a distance, 400, to make our team do 400s. We would get a little wheel and get out there before the class got there, and we would roll the little wheel out. But the wheel is going like this, so you know what I'm talking about if you run. You've seen your coaches with this before. But we actually will walk the little wheel out to mark the track. So does everybody understand that there's an arc length unwrapping onto the ground? I didn't have much success with the tape, even with, I think, Rebecca's help the other day. So I'm going to try another roll of tape and hope for better. Oh, good. This is going to be good. So as this rolls, do you see I can say it went 5 miles per hour? Now, where did the 5 miles come from? It came off of this. This is the circumference, or the arc length unwrapping. So kind of get over the fact that arc length can just be like this. Arc length is just a fraction of the circumference, but it can be 85 times the circumference, okay? If this, hang on, I'll get your questions in a minute. A wheel has angular velocity. By the way, I'll show you the Earth. The Earth has velocity too. Things can spin at different rates. So let me ask you some questions, then I'll answer your questions. Please don't forget them. But I want to keep fluid with this conversation. So, if you can't really see, can y'all see that the yellow is much smaller than the orange? I mean, it doesn't look like it like this, but y'all see there's like a little small, everybody see what I mean? So it's significantly smaller, it's about that big, okay? How could the yellow keep up with the orange? Again, I should have grabbed it. It's got to spin faster. So when we say, is it going faster, we kind of mean what we say and say what we mean. When you say it's going faster, you're talking about feet per second and miles per hour. You're not talking about how fast it's spinning. Do y'all see the difference? So girls, there's angular velocity and linear velocity, okay? So this one would have to spin faster. If they're spinning at the same rate, would you agree the orange would go faster?
Yes.
Okay, because you would have gone, oh, well, that one just went 6 miles an hour, and this one may have just gone 4.5 miles an hour because it's got a smaller radius. So radius is a big deal. Spinning is a big deal. Spinning is angular velocity. Stay with me. Angular velocity is dimensionless. Couldn't this spin 360 degrees per second? This one could spin 360 degrees per minute. Okay? Remember how I told you a while back, and I said it was going to be important later on, degrees and radians are dimensionless. We could get in an airplane and turn 30 degrees. The Earth can turn 30 degrees. I could draw a little 30-degree angle on my piece of paper. They're all 30 degrees, but they're all different measurements as far as the sides of the angle are concerned. Do y'all see when I say 30 degrees? You have no concept of what the lengths of the sides are yet. The lengths of the sides make a big, big difference. The circumference makes a big, big difference, or the radius, okay? So what's the only way for two wheels to go the same speed? There's two ways, or maybe three. What are some ways that two wheels can go the same speed? What's one?
Same radius.
They have the same radius, but does that mean they're going the same speed?
That's what it's,
It goes.
Dana?
is it that they're going the same revolutions per minute?
They're going the same revolutions per minute. So if they're the same size and they're spinning the same speed, they will go the same they'll go the same linear speed.
So you could say if it has the same radius and it goes the same distance, then it's going the same speed.
If it has the same radius and they went the same distance in the same amount of time.
Yes.
Okay. Yeah, so if they have the same angular velocity and the same radius. Are y'all with me there? That's what Zayna and I are saying, and Chloe. Y'all see what I mean? So what's another way for two wheels to have the same speed? We're talking feet per second, miles per hour, Rebecca?
Let's say like one wheel is smaller radius-wise than the other one. The smaller wheel will have to have a higher angular velocity than the larger.
Okay. Now let me take some questions before I move on. There were hands in the air. Are your questions like over, Ghana or Della?
So when you were like unrolling the orange tape or ribbon or whatever it is,
I don't know what it is either. It's not sticky, thank goodness. Okay.
if you were like pulling it like the ribbon at the same rate, but
Like both of them or
just the orange,
just the orange? Okay.
as like the ribbon unwrapped, would it like even if you were pulling it at the same rate, would it be technically going slower?
It
Because
would.
the radius is smaller.
I don't know which it you're talking
the
about.
radius is
roll.
Oh, yes, it would, thank you. We're talking about a tire rolling down the street. The tire's not shrinking, like my roller tape would be shrinking.
I was
Yeah.
just like thinking.
Yeah,
because of the
it
tape.
sure would. That would be ever variable. That would be ever aggravating. So, great. Well, y'all are coming up with some great questions I haven't faced before. So this is good. Yes, that's not going to happen. So it'd be a great bonus question. But there would be the limit of that. Okay. Anyway, Elena.
So angular velocity is just how many like degrees or radians it turns.
Yes. Angular velocity is what Zayna said. It's revolutions per second, minute, whatever.
Okay.
It's how many degrees or radians. We're going to work in radians mostly,
Okay.
and you'll see that in just a minute. But you can work in degrees and convert it to radians, so we'll look at different. But it's how fast it's spinning. So if you can imagine a little gear spinning really fast and a big gear spinning really fast. Now I want to go to something else. Simple machinery. And let's go back to these gifts, and maybe I can get one that's you can see. Bicycles are a great example of this. But this is what we're about to talk about is all over the place. Wow, it's a lot of math on what I'm about to show you. And it's not that I'm so super hung up on bikes, but it's a great example of what all's happening. I have no idea what's going to happen here. I haven't vetted this video, so I hope there's no bad words in it.
Gear ratios are a hot topic. And I'm not even joking. It's actually quite a fascinating subject once you start to understand the ins and outs. Now, what I'm talking about are the number of teeth you've got here down the cassette and up here on the chainring. Differences in the number of teeth and the combination of the two will make a massive difference as to how far you can ride and what kind of gradient you can ride up.
Okay. So, I don't know how many of you bike, probably many of you do, and some of you, if you're not already into like triathlons or at the gym on the stationary bike, I'm sorry I laughed because I'm not a gym person. I run by in like weather or rain or whatever and look at all the people like on these machines and I'm just like, I don't get it. But anyway, which is bad because when I'm injured, I'm really not good about going to the gym. I rather be outside. But in any event, if you're into triathlons or something, you realize, you can hit speeds of probably 30 and 40 miles an hour, that you're trying to go faster and faster. Girls, human beings cannot make their legs go 40 miles an hour. Okay? Like, I need to look up, I don't know actually, this is embarrassing. Like the winner, the female winner of the marathon Sunday, I think was 2:22. And so I don't know what that translates into miles per hour. We can figure that out. What's 26 miles in 2 hours? Let's do, what's 13 miles an hour would be like the men's run about a 2-hour marathon. Did you see the guy just broke it with the Nike thing, but they won't count it. Anyway, it was behind a pace car and a lot of people drafting it. It was not in marathon conditions. It was like but it's still cool, like keep it under 2 hours. Okay, so these people, these guys and girls, I mean, the men are running, Pierre and I, Pierre was looking up while we were talking yesterday. It's like they're running sub 5-minute miles the entire time, 26 miles. Think of trying to run a 450 mile once, much less 26 times. So they were roughly going 13 miles an hour. They're the fastest in the world. So how can a person on a bicycle go 30 miles an hour if the fastest runner, well, you're going to bicycle for hours at 30 miles an hour. The way it happens is your feet would have to be going like this. They'd have to be going twice as fast as the best marathon runner in the whole world. Y'all see what I mean? You can't do that. So we have machines to let us do things. You know, like simple levers that I can't lift something heavy, but for some reason when I put in a lever and push stand on that, then I can lift it, okay? So we have all these nice machines. What happens is this person is leisurely pedaling this, or maybe aggressively pedaling. Maybe let's say 13 miles an hour, okay? They figured out all these gear ratios. You may have seen that big table I pulled up a minute ago. So here's your feet. Your feet are not doing this work. It's really ingenious what they've done. So they have this connected to this tiny thing. So this is like tying me to Lauren Heskett. Sorry, I know she's so tired of me. I'll tie myself to Inez, okay? So it's Vanessa's best marathon's 2:38. Mine was 3:24. And so if you tied me to it, and now it's not that today if you followed me on Sunday, but some of you don't follow me on Sunday. Don't even look it up. It was on the screen, but it was done. All right, so keep it on. So anyway, if you tied me to Inez, and Inez, a lot of y'all know who Inez is? Yes. She helps coach track.
I love her.
Here. She was a world-class marathon runner. And she's like, hey, you're the best person on the hallway. But, and would you agree? Oh, she's awesome. Anyway, she had really cute boots on yesterday too. She got new red boots in London. Okay, so anyway, did anybody see Inez's red boots yesterday?
Yeah.
Oh,
Her heritage.
yeah. Look really good. Okay, so anyway, if you tied me to Inez and Inez took off, what would I have to be doing? My feet would have to be going, and she's just running. Do y'all see what I mean? Okay, now I'm getting a little bit like silly as usual. But if I tie this to a smaller roll of tape, and I start to turn this just sort of leisurely, what's that little?
The little tips are like,
Yeah, if I have a little roll of tape. Can y'all do that? Do y'all see what I mean? If I attach this and start to turn this and I have them by a chain, Let me tell you what I've just made. As soon as I tie them together or chain them together, they are chained together. It's just like if you put something around my wrist and take off, okay? Or grab a little kid by the hand and start running, all right? I did mine sometime when I was aggravated at. But anyway, now they're both like 6'2", so that doesn't work. But anyway, as I turn this one, girls, they have to have the same linear velocity. Do y'all see that? They do. Look. As this one turns just a bit, and this one gonna have to turn a lot to keep up with it. They have the same linear velocity. Does everybody see what I mean? So this is a line. This is a line. So it doesn't matter if it's like this, is it? A chain is still a line. We've all had our chain fall off of a bicycle and see a little line laying around we have to put back on. Maybe you haven't, I don't know, I haven't. But anyway, these have the same linear velocity. It's very, very ingenious what they've done. And this little guy's having to keep up with this big guy. Now these are not very different. These are a lot different. Do y'all see that? These are a lot different. So as I'm pulling this, just got right in my bike. What's this person doing back here? It is bolted to that big tire. So it's different being chained and being bolted. Okay? If you're bolted together, you have the same angular velocity. Do y'all see what I mean? If you're bolted together, they do not have the same arc length. Do y'all see that? Different radii. But they bolted it to that, so while this is spinning fast, what's this one happen to do? Then they cover in lots of ground because it's different radius. So before we go on, these have the same, they're chained together, they have the same linear velocity. These are bolted together. They do not cover the same ground. They have the same angular velocity. Okay? It's like this. If I went to the playground with you and I spun that thing that goes around like this, with you on it, you are going the speed of that playground equipment. Do y'all see what I mean? If you put like a little circle in the middle of it, they're going the same angular velocity. But if you're toward the center of that and your friend's hanging out on the end, your friend's you can feel that centrifugal force a little bit more. The person on the outside's going faster than the person on the inside. Because aren't they they're covering this, you're both going the same amount of revolutions, but you're on the outside, so you're going faster. Lots of things, okay? So lots of questions, Elena?
So the big gear and the tiny gear attached to the wheel, like they're going technically the same speed, but that the small gear is a bigger angular velocity.
Yes. Which is why they do it that way, okay? And now, we're not even getting into this. They're smart enough to know how to change these gears to make you go different speeds. Like in the small one, you might be going up a hill because it takes less work. And then you can change gears and go to different, you're just changing the radius of that back gear, okay? So anyway, it's interesting to think about. Your mind's probably racing through all of that. Let me show you, all right, question? Oh, hurry. Don't forget where you are in this. All right, now, I don't like that one. I thought this was going to go.
So true.
I'll move on. I can't find what I'm looking for, but you see, don't you have to really chain them together? as long as they're linked together, you've all seen gears moving, maybe not paid a whole lot of attention. But if this one starts to spin fast, this one's gonna have to keep up with it. Do y'all see what I mean? Because they're attached together. Look at how they're attached together. Aren't they linked together the way they've gotta have the same arc length? So as this one may be lazily spinning and cover 30 degrees, how is that one gonna keep up? It's probably gonna have to cover more degrees to keep up because it's smaller.
And is that like in a ratio that does it?
It's a ratio. There's a definite ratio that people are doing this that know what they're doing. Okay. So anyway, let's move on and do some problems. So let me pass these out. Wherever they are. I hope I brought them downstairs. So grab one of these and pass it around. Okay. Here, I'll spread them out. Okay. Are there any lingering questions before I move on of what you were maybe going to ask? Okay. All right, so as you're passing those around, you can kind of look up here also. If I have a gear, okay, and another gear, and it depends on what I want to do, okay? I then get a line and I chain them together with a belt. Y'all have probably heard that word before. If you open the hood of your car or a cab, there's actually belts that are in there, like rubbery kind of belts that are joining things together, okay? And as this one now starts to spin through a certain arc length, watch, this chain is going to be pulled like this, which is going to pull it like this, which is going to pull it like this. Do y'all see they have to go through the same arc length? Is that okay with everybody? That's the same S if you're joined together, okay? If I bolt something big onto the back of it, and these are bolted together now, as this one spins, this one's going to spin through the same, sorry, that's not right. As these spin, they're going to have the same angular velocity. If this one's spinning 180 degrees per second, this one's bolted to it. It's going to have to spin 180 degrees per minute. Once you are bolted to something that's spinning, you are going to spin that fast, okay? All right. So now one other thing I wanted just to show you, and then we'll move on. It's just interesting to look at some things that, that spin. So I'm going to put in the angular velocity. Of the Earth. And look how it comes up in what kind of measurement. It takes the Earth approximately, we knew this, 24 hours to make one complete revolution. But what did they give us the speed in? The angular velocity in what? Radians per second, okay? But we're already doing circumference and angles many times in radians anyway, based on your homework, all right? So what about the angular velocity of a DVD? I haven't tried this. Let's see what it says. So 570 revolutions per minute, rotations per minute, sorry. So let's get our definitions or our terminology right. I hate the word definition. I don't know why I just didn't like learning definitions. Terminology, our language right. A rotation and a revolution can easily be converted into radians or degrees. Okay? Okay? RPM does not mean radians per minute. It means revolutions per minute. It's like MPH that we're used to, miles per hour. RPM is revolutions per minute. If we want something else, we'll have to find it. But every revolution gives us 2 pi radians. Would you agree with that? Yeah. All right, does everybody have a sheet? Okay, so angular velocity is how fast something's spinning, not how fast it's going. So let's do number 1. And let me find my sheet. Did anybody get my sheet with my work on it? Here it is. Okay. Number 1. We're going to work these all together. All right, so number 1. A tire for a compact car is 22 inches in diameter. So a small car has a radius of about 11 inches. Underline the word diameter. Watch out on tests and quizzes and homeworks. You need the radius. If I give you the radius, use the radius. If I give you the diameter, make sure you use the radius. Okay? So above that on my sheet, I wrote 11 inches above the 22. If the car is traveling at a rate of 60 miles per hour, 60 miles per hour, that is S. That is its linear speed. S equals R theta, all right? As this tire moves, how in the world is it going to go 60 miles in 1 hour? Do you see that it would have had to start rolling and leaving its circumference or arc length on the ground behind it? So that how fast you are going, your traditional speed, is linear velocity. Linear velocity is how much ground you covered. I've tried to show you in many different ways with tape and snow and stuff like that. But y'all see why we call that a linear speed? That's what you and I talk about all the time. 13 miles an hour, 9 feet per second. That is S equals R theta. Okay? So find the number of revolutions the tire is making per minute. Let's just slow down. Take your given information, and you know it's going 60 miles per hour. And the speed is S equals R theta. So I have 11 inches theta. I like to do this really slowly. You can do more in your head if you want to, but I don't suggest it. All right, I want to find the number of revolutions. Do y'all see how if I can get to theta, I could probably figure out the revolutions? Theta has everything to do with how fast it's spinning. Angular velocity, okay? By the way, girls, these are all things you've heard. Miles per hour is S, linear speed, okay? Revolutions per minute, you have no idea how far it's gone. You just know how fast it's spinning. That's angular velocity. Katie?
So theta in this case is how many times it rotated, to go 60.
Let me work the problem and you'll see, okay? You'll see, I promise. I'm gonna solve for theta and answer Katie's question. I'm gonna divide by 1 over 11 inches. And would y'all agree that's solved for theta? I can't divide miles by inches though, so I'm gonna have to use some conversions from my other classes, okay? So I'm gonna say 60 miles per hour times 1 over 11 inches. Then I'm gonna go to 12 inches in 1 foot. Inches are gone. And then I'm going to go from feet to miles. Does anybody remember how many feet are in a mile? 5,280 feet and 1 mile. Now watch what happens, Katie and everybody else. My feet are gone, my miles are gone, and that's a bit unsettling because you just got something per hour, right? Do y'all see what I mean? Do y'all have any words on the top? There's no words on the top. What was theta in if you're using S equals R theta? Radians. So this is this number in radians per hour. All right, if you want to get out your calculators, and in parentheses I would put 60. I don't like to keep up with the numbers as I go. I just do it all at once. 60 times 12 times 5280. Divided by 11, and right now I just have 1 and 1, but I would put all of my numerators in parentheses divided by all of my denominators in parentheses. All right, can someone get that number for me? I think it's 5,760.
Yeah.
5,760 radians per hour. Now let's talk about how this radians just popped out at us. Hang on just a minute, I'll come back. let me keep talking because I clear up a lot of stuff. If I do that, please answer your question as I forge ahead. Remember how I said radians are dimensionless? Degrees are dimensionless, okay? I can turn 180 degrees. I can turn 180 degrees. You can turn that bottle 180 degrees. It's dimensionless, okay? That's like a ghost. It doesn't have a dimension. It can come in and out of the problem, okay? So I knew that if I used the formula S equals R theta, I was already working in what? Radians. I could have used another formula that was based on degrees, like a fraction of a circle. But if I'm using pi r squared and 2 pi r and S equals R theta, I'm already working in radians. So all of the dimensions should have disappeared because now it's only talking about how fast it's spinning. Do y'all see the difference? Now it's only talking about how fast it's spinning. All of those miles and feet should have disappeared. They don't matter in theta. Let's look back up here. R theta. Something could be spinning, but doesn't the radius make it go a certain speed? Do y'all see what I mean as my radius gets bigger? But it's spinning the same. So I'm just looking for theta, which is in radians per minute. I'm going to finish the problem, then I'll come back and take questions. I wanted it in RPM, revolutions per minute. So let's go a little bit more. Okay? One revolution has how many radians? 2 pi radians.
Miss Terry, it's not 5,760. I got 345,600.
Okay, maybe that's the final answer. Thank you so much. Thank you for also insisting that I listen to you. So, because I was going to probably, maybe the answers. No, I got 5,760.
I think you thought it was.
Oh, I've already converted it to minutes, maybe.
Yeah.
Okay, so let's stay with yours. Sorry about that, girls. Katie, what'd you get?
345,600.
3, 4, 5,
600.
600. Thank you. Thank you for that. May be what a bunch of people were trying to tell me. Okay, and then you got to be like Katie and just shout it out because she's used to me and she's like, I do this all the time. Okay, I thought y'all had questions. Sorry about that. I was so on a tear
I don't
about.
understand how it's not 5,760, because that's what I got.
60 times 12 times 5,000.
60 times 12 times 50, 280 divided by 11.
It's gotta be huge because 12 divided by 11 is like
63,360 divided by 11.
I think you thought it was 2. Like 60 times 2 times 52.
do it again, you have to.
I did.
Well, you're
Wait,
saying
here,
radians.
here, let me see your calculator.
Yeah, I'm sure about this.
We got to reconcile this.
You get the
Did
number.
you do 60
Well, I might not
times
have
12
times
times
60.
5?
I
280
just
divided
got
by
it.
I might not have multiplied by 60, too.
I think that's.
Oh, I don't think you put the 60 in.
Yeah, I did it for 60.
Yeah, because I'm just looking at it like, if you don't put the 60 in, this 12 and 11 is kind of a wash, and so it should be. Anyway,
Yeah.
thank you. So, girls, we just got to be careful to punch it in correctly in our calculator. And I'm sorry, I had gone forward into going ahead and solving the problem. So now let's keep going. I want, most people speak in RPM, so if you're in a job and somebody wants to know how fast something's spinning, they probably don't want you to hand them radians per hour unless they ask you for that. They probably want revolutions per minute because it's probably what they're going to program into a computer or something. So let's go to revolutions per minute. So one revolution has what? And girls, it's real important that you realize it's 2 pi. You've got to put that together, okay? 2 pi radians. So now my radians cancel. And the last thing I want to do is 1 hour has what? 60 minutes. So my hours are gone. And do we now have RPM? Do y'all see the words left on the top is revolutions, and the word on the bottom is minute. You can call that RPM. That's revolutions per minute, and I believe that one should be 5,760. We okay? All right, there were a bunch of hands going up, maybe to correct me. Do you still have a question?
Yeah.
Okay.
So the R length is the same as the revolutions per minute? Or the
No.
no,
Theta
no,
is
yeah.
your angular velocity, and it's in actually in radians. If somebody gives you RPM, you've got to convert it to radians before you use it.
Okay. So, but the arc length is the same as the linear velocity.
Yes, the speed, feet per second, miles per hour is S. So this is how fast you're going, which is convenient because S is sort of like speed. How fast it's spinning combined with how big the tire is makes you go a certain speed. All right, so this is linear velocity right here. That's why I've taken such great pains with tire tracks and mud and tape that you actually see this line unwrapping from a circle. This is how fast it's spinning. This is its angular velocity. Okay, let's take another couple of questions because I want to get a couple more examples in before we go. I think it will clear up a lot of things if I keep moving. So quickly, Grace?
Do you divide by 2 pi? Do you do like?
I said 3,560 in parentheses, or whatever that word is, divided by parentheses 2 pi times 60.
That's
I didn't get that.
I think the last.
Oh, you guys, I'm sorry, I'm totally messing up. Thank you, it would help a lot if I didn't mess up this problem. I remember now. If you, I must have on my paper did this next, and then did that last. And you do get 916.72 RPM.
Wait, I got 9,047.
I got 916.
Okay, so let's all do this. Clear your calculator. Clear your calculator. All right, now in parentheses, open parentheses, 3, 4, 5, 6, that's really cute, 0, 0. 3, 4, 5, 6, 0, 0, close parentheses, divided by open parentheses, 2 pi times 60. Close parentheses, enter. That should give you 916. Girls, don't ever avoid, you should start throwing things at me since I've already made at least 2 mistakes on this problem. So hopefully you'll still listen to me and I have mild bad behavior. Don't ever do something like divided by 2 pi without parentheses. If you say, we're used to seeing 2 pi, your calculator thinks you're dividing by 2 and then multiplying by pi. Don't ever type in something like 16 over 2 pi into your calculator. It'll find 8 pi. It'll say 16 divided, it's going to do this. 16 divided by 2. Do y'all see what it's going to do? You've got to tell it that you're dividing by 2 pi. All right, big deal. I'm going to move on with like 1 minute left. All right, let's go to number 2. A wheel with a radius of 9 inches. I underlined the word radius for myself. Revolving at a rate of 2,400 RPM. Find the angular speed of the wheel. So angular speed is always in radians per minute when I ask for angular speed. So Katie, we're on our way to that. If I'm going 2,400 revolutions per minute, how fast is it revolving? We usually say it in degrees or radians. We always say it in radians in my class, okay? Katie, just keep watching. I'm going to get your questions, okay? How many radians are in 1 revolution? All right, so 2 pi radians in 1 revolution. Revolutions are canceled, and I get 4,800 pi radians per minute. Now, going back to Katie's question, if I've already told you it's 2,400 RPM, angular speed has got to be in radians or you can't use it in the formula. What have you learned about S equals R theta? I can hand you revolutions all day long, okay? But what do you have to use in the formula? Radians. So that's hard to get, I understand. That's why we only done 2 problems today. Only why I only had 4 printed out, okay? Did y'all see what Katie and I are talking about? Radians, angular velocity can be revolutions per minute, but you can't put it in the formula to convert it to radians. Now, this is the angular velocity right here. Angular velocity is at S, R, or theta. Angular velocity, S, that's the theta. So the second question, find the linear speed of the wheel. The radius of the wheel is 9 inches, and theta is 4,800 pi radians per minute. I didn't say it in this problem, but I wanted the speed in miles per hour. What are we going to do at the top as we start to pack up? Inches and radians and minutes. I got too many dimensions going on. Which one can I get rid of? Which one's dimensionless? Radians. I needed it to be in radians, but now I can just ignore that word. It's a ghost. It can come in and out of the problem as I need to. Hey girls, it's mainly there to make sure you're in radians. Now you all can change inches to minute into miles per hour for the rest of the problem. Your homework is a quiz. Pack up and leave. Your homework is a quiz, and probably some problems out of the book, and try to finish the worksheet. Okay. Number 4 will be a bit challenging, but you won't have much homework. See me if you need help. It's a memo quiz. Good question.
Mrs. Eric